All right. I hope everyone's doing well. We are getting ready for exam number two. So that's going to be chapters 25, 24 and 25. So Gauss law and then electric potential. So this is going to be similar to last time. Mostly what I'm going to do is give you an overview because it's a lot of formulas, a lot of equations, a lot of concepts. So first and foremost, I want the review to be a place where you see everything and understand exactly why we're looking at the things we're looking at, just so it's all in one organized place. For the purpose of chapter 24 and chapter 25, I actually think that practice problems are going to be a little bit more beneficial. So at the very end, I will be doing two or three practice problems. So, so if you don't totally get something in the formulas slash overview review portion, then don't worry, we're going to do some problems. So I'm going to start with chapter 24 here. Chapter 24. So this is going to be our Gauss law and electric flux. Okay. So let's start with electric flux. So what is that? So electric flux is a mathematical quantity. We write it as this psi here with a subscript E to say that we're talking about electric flux. And it's going to be defined as E dot A. Just like I usually do, let's just define what all these quantities mean. So this is electric flux. I like to think about it as the amount of electric field. Some people also say electric field lines that pass through a surface. Electric flux is really, really important. It's going to have units of newtons per coulomb times meters squared. Next quantity here is the electric field. Electric field has units of newtons per coulomb. And last but not least, we have area here, units of meters squared. And as a couple side notes, this is a dot product here. So a dot product, you may remember, if I have two vectors, A dotted with B, that can be rewritten as the magnitude of A times the magnitude of B cosine of theta. So same thing up here. Electric flux is the electric field passing through the surface, dotted with the area of that surface. That can be rewritten as the magnitude of the electric field passing it times the area of our surface times cosine of theta, where we want to be really particular. This theta is the angle between the electric field and our normal vector. So angle between E field and normal vector. All the normal vector is it's the vector that's pointing perpendicular to the surface we're looking at. So for instance, if I have a surface here, oh, that's terrible. And I have an electric field passing through it. Here's my electric field vector. And then my normal vector is just going to be perpendicular to the surface. This here is the angle theta that we use for our dot product. So as you do problems, you're going to have different surfaces. Most of the time when you do electric flux, it's just going to be what direction is my electric field? Let me use the dot product with the area vector, and we're all good there. In this case, if you see a box like this, the area is just going to be, let's say this is side B and side A. The area is just going to be B times A. If you have more complicated surfaces like a sphere, I'll just tell you that the area of a sphere is 4 pi r squared, where r is the radius. And if you have another common one, which is cylinders, the area is going to be pi r squared times L, where L is the length of the cylinder. So these are two area equations to keep in mind. We're going to see them a lot when we look at flux. So keep these in mind. Before I move on to the next equation for electric flux, I do want to put out here that this electric flux equation in its most general form is written as an integral. So you may have seen this. Electric flux is the integral of E dot dA. So this is the form of electric flux most generally. So this is general form. And when the electric field is constant with respect to area, that's when we can simplify this to E dot A. So just make sure you understand. You can simplify it from its most general form if and only if E field is constant with area. Okay. That is the first part of electric flux. I'll just put a little note around this. This is important equation number 1. We have a second equation for electric flux. It's that the electric flux equals Q enclosed over epsilon naught. So first things first, this is only true for closed surfaces. By closed surface, I mean a sphere or a cylinder. What an example of a non-closed surface would be something like a plane or a line, something like that. Again, that's electric flux here. Oops. This charge enclosed is just the amount of charge inside the surface, or the object rather, I should say, inside the object. And that has units of coulombs. Epsilon not down here, you've been using the whole time. That's just a constant. It's equal to 8.85 times 10 to the negative 12. So these are our two equations for electric flux. I'm going to write them again down here as a summary just because they're so important. So we have electric flux equals the integral of E dot dA. And when we have a constant electric field, we can just say that that's E dot A. Another form of electric flux is the charge enclosed by a closed surface over epsilon naught. All right. Before I move on, any questions about electric flux, how to apply it, what any of this stuff means? Cool. Okay. So that's about already 80% of chapter 24 are going to be questions involved and stuff like this. Now, last but not least is Gauss's law. All Gauss's law is we're going to set these two flux equations equal to each other. So we're going to say electric flux equals electric flux. And that means that the integral of E dot dA is Q enclosed over epsilon naught. And this is Gauss's law. So I do want to pause for a second and just mention why we use this, why this is important. So all Gauss's law is it's a concept on electric flux. It's basically a mathematical model that allows us to find the electric field of different charge distributions. So this is a mathematical model or formula that easily allows us to find the electric field of complicated distributions. E field of complicated objects. So at the very end here, once I go over chapter 25, I'm going to do some Gauss law stuff, some Gauss law practice problems where I show how to use this. That's because this equation as it is doesn't seem too bad, but applying it has its own set of rules and things to keep in mind. So I'm just going to leave this here for now. When I go through the problems, I'm going to basically show you how to tackle Gauss law problems. Before I do, I'm going to make a tiny little note here. This is at the end of chapter 24. And I just want you to remind you about conductors. So just as a reminder, this is going to be important a little bit later. Conductors store charge at the surface, and the electric field inside a conductor is always 0. Lastly, we only use Gauss's law on symmetrical objects. So the only objects you are going to see in this class and on your test are going to be spheres or spherical shells. You'll also see cylinders, and you may see boxes, but that's it. Cool. All right. So funnily enough, that is literally everything for chapter 24. Does anyone have any questions before I go to chapter 25? Cool. Again, most of chapter 24 is practically how do I apply this to problems. So I think most of your questions are going to be answered when we actually go through it. All right. So chapter 25. This is electric potential. and potential energy. So in this chapter, there's two main problems you're going to see. You're either going to have to deal with point charge and point charge distributions, or you're going to work with conductors or capacitors, sorry. So I'm going to start with the capacitor picture, and I'm just going to kind of set the tone here. So let's say we have a capacitor, and all that is a plate with positive charges on one side and negative charges on the other. Now let's say I place a positive charge here. So this is positive Q. Now, we know that the electric field is going to point from the positive plate to the negative plate, and it's going to be constant. So this is our constant electric field, which we'll note as E. We also know that a positive charge is going to feel a force in the same direction as the electric field. So this is going to feel a force going this way. Now let's say our charge is going to start at an initial position here, we'll call X initial, and then it's going to end on the negative plate at X final. So instead of using the force and electric field picture, we're going to switch into trying to describe this using energy. If you recall from Physics 195, work is equal to the negative change in potential energy. We also know that work is equal to the force times the displacement, so delta X. So in this case, instead of talking about gravitational potential energy, we're going to try and define electric potential energy. So we're going to have this as the electric force that acts on our particle times the displacement, which is just X final minus X initial. And that's going to equal negative change in potential energy. Now, my electric force, we know from the first chapter, can be written as our charge times the electric field that it feels. So substituting that in, we have Q times E times our displacement equals negative change in potential energy. I'm going to put the negative sign on the other side here, and we have the change in potential energy equals Q, E, and then instead of X final minus X initial, I'm going to make this our displacement, which is usually written as D. And the negative sign's right here. So what we just proved here is that for a capacitor, which is two equal and opposite plates, so this is positive Q, this is negative Q, the electric potential energy or change in electric potential energy is equal to negative Q times the electric field between the two plates times the displacement between the two plates. Now we also have a special name for this here. This is Q, and this is now something called the electric potential, which we note with a V. And this is technically change in potential. Okay. So all the equations I'm writing right now, these are all true for a capacitor setup, and we're going to be doing a lot of capacitor problems, so these are important. So I just described what the electric potential is. So this is mu F minus Ui, change in electric potential energy. This has units of joules because it's an energy. Q is the charge that's in our capacitor. It has units of coulombs. And then this new quantity, delta V, is the electric potential. And that has units of volts, which is just joules per coulomb. Cool. And I should note this is change in electric potential. So just to make a little summary here, and this again is for capacitor problems. For capacitors, first thing we're going to note, change in potential energy is just charge times change in potential. And we also know that change in potential energy equals negative electric field times your displacement, d. And just to remind you, d is your final position minus your initial position. So if and when you see a capacitor on the test, go right to here, remember your work equations. Past that, it's just conservation of energy as you would in Physics 195. All right. So this is the first part of the picture. This is dealing with capacitors. This is the first sort of main setup we see. The second main setup is going to be charged particle distributions. So charged particles. So switching gears here. If I have, let's say, a particle here, and it's charged to positive Q, I can define a point that's a distance r away from my charged particle. And you'll just have to believe me that at that point we can define the electric potential V to be K Q over R. Again, this is for point charges. If I have multiple point charges and I want to find, let's say, the net potential at some point, then it's just the sum of the individual potentials. Again, a lot of this is going to become clear when I do the practice problems. K is the Coulomb constant. It's our 9 times 10 to the 9. Q is going to be our charge in coulombs. And R, very especially, is going to be the distance from charge to the point of interest. And here I'll just state, if you have multiple charges, you pick what your point of interest is, and you sum up all the individual potentials from each charge. So that's what's called superposition. position. But all that means is we can add up all the individual charges. Cool. Last but not least is electric potential energy of charged particles. So if I have, let's say, two particles in space here, I'm going to call this Q1 and this Q2. The electric potential energy between those two particles, which we note with a U, is just K, Q1, Q2, over the distance between them, which I'm going to call R12. Again, this is the electric potential energy. Electric potential energy. It has units of joules. This is for particles only. Q1 and Q2 are our charges, and then R12 is just the distance between them. If I have multiple charges, things do get a little interesting. Instead of electric potential, where I pick a point and I define my distance to be from each charge to that point, for electric potential energy, it's a little bit different. I want to sum up all the pairs at K, Qi, Qj, Rij. All that means is, let's say I added a third charge down here, Q3. To find the potential energy of this system, so if I wanted to find, sorry, let me put system down here. If I wanted the potential energy of this system up there, it's going to be K, I'm sorry, it's going to be the potential energy between 1 and 2 plus the potential energy from 1 and 3 plus the potential energy from 2 and 3. Whereas for electric potential up here, if I added a particle here, let's say this is Q1, this is Q2, my net potential would just be the potential from 1 here plus the potential from 2, where both of them, like this is R1, this is R2, are going to be defined at that point. Whereas this is R23, this is R13. Cool. So subtle distinction between finding the electric potential and electric potential energy for a system of point charges. Okay. So the funny thing is, as hard as this chapter seems, that's literally it. So to summarize everything, for charged particles here, we just have electric potential energy is U equals K Q1 Q2 over R12. And if I have multiple, it's just going to be the sum of the pairs K, Qi, Qj, Rij. If I have electric potential here, It's just K Q1 over R. These are both for our particles. And then for our capacitors, we have electric potential energy is negative Q, or I'm sorry, is positive Q times potential. And technically this should be change and change. And we have our electric potential difference equals negative electric field times our displacement D. So this is all of chapter 25 is just these four equations. All right. Any questions? Ooh, scroll back up. You got it. No questions. That was all pretty good. Or you got to see this done in practice to understand. Oh, gotcha. Okay. If you guys have everything, I'm gonna post these notes later. So if you don't have it, don't worry. It's gonna get posted. And let's use the rest of the time to work on practice problems because as you can see, there's a very limited number of formulas here, but in practice, as I'm sure you know when you did your homework, when you actually apply it, it's actually really difficult. So, Alberto has a good question. So while doing the homework, some of the equations lost their negative sign. Yeah, so there is a good reason for that. It depends on a couple things. So, I guess we can just I'll say this. This is kind of the easiest way to think about why that negative sign will change. So if we go up to this capacitor picture here, what Alberto's saying is in some of the equations, you're going to see this negative sign here, and in some of the equations, you're not going to see it. So that has everything to do with if you have a positive particle or a negative particle. That's all it is. So if you have a positive particle, it's going to be these exact equations that I laid out for you. If you have a negative particle, then you just add a negative sign.
So
That's
if it's negative, is the potential energy going to be positive then?
yes. It basically
Okay.
flips. We can do one of those problems though, just to clear that up. All right, so let's do I guess let's start with chapter 25. I think that these problems are going to be a little bit faster. Chapter 25. So I'm going to do one capacitor problem and then one sort of group of charges based problem. So a common thing for capacitors or a common problem is going to be we have a capacitor here. Here it is. We got positive charges on this side, negative charges on this side. They might give us, say, there's a proton right here. So our proton is going to start at rest on the positive plate. They may give us, let's say, the electric field that points from positive to negative here. is 2,000 newtons per coulomb. They also give us that the spacing D is, say, 2 centimeters. D is 2 centimeters. And they may ask, what is the speed of the proton when it reaches the negative plate? All right. So how we go about these problems is very similar to how you did conservation of energy problems in Physics 195. So first things first, I want to define where I am initially and where I am finally. So our proton starts at rest on this positive plate. So I'm going to call that my initial position. Then it's going to feel this electric field or this push on the positive plate. Simultaneously, it's feeling a pull from the negative plate, and that's going to cause it to accelerate, and it's going to end right here. So that's going to be my X final. So I know the electric force is conservative, so I can use conservation of energy, which states that my initial kinetic energy plus my initial potential energy equals final kinetic energy plus final potential energy. Where in this case, instead of working with our usual gravity, which is mgh, we're working with electric potential, which we know is Q times V. V is potential. I'm going to do this same problem with an electron after so you guys can see the difference between the two. Okay. So the proton starts at rest here at our initial position. So that tells me that the initial kinetic energy is 0. Now, I don't know what the initial potential energy is, but I can subtract it on both sides. So I'll have 0 equals kinetic energy final plus potential energy final minus potential energy initial. The reason I did that is I know that my final potential energy minus my initial potential energy for a capacitor system is equal to, and I should keep writing this, I'm sorry, is equal to the change in potential energy. And I know that the change in potential energy in a capacitor is equal to the charge of my particle times the change in potential, electric potential, that is. So I can rewrite this as 0 equals 0 equals final kinetic energy plus Q delta V, or change in electric potential. I also know from my above problems or my above formulas that I'm not given electric potential in this problem. I'm given electric field. So the way to go from electric potential to electric field in a capacitor is noting that the electric potential equals the negative electric field times the displacement. So in this case, that means the change in electric potential is negative 2,000 newtons per coulomb times our displacement, which is 2 centimeters. So first things first, some of you guys might be like, our units don't cancel. What's going on here? As a little side note, we actually have two different ways of writing the units for electric field, and they're identical. So electric field units can be newtons per coulomb. And we had that when we were looking at the force picture. So E was force over charge, so that's why we had newtons per coulomb. Identically, the electric field units are volts per meter. And we get that because the electric field is equal to the potential or change in potential over distance. So these are exactly the same. If I write 2000 newtons per coulomb, it's the same thing as writing 2000 volts per meter. So I'm going to change these units just so they cancel a little bit better. I'm going to write negative 2000 newtons per coulomb is volts per meter. And that's times 2 times 10 to the negative 2 meters. So now the meters cancel here. So that's going to be negative 40 volts. So plugging that back in, we have 0 equals the final kinetic energy of our proton when it's at the negative plate. That's going to be equal to the charge of our proton, Q, times the change in electric potential, which is negative 40 volts. So I'm going to put the negative 40 times Q on the other side. And I'm going to note that the charge of a proton is 1.6 times 10 to the negative 19 coulombs times 40 volts. And that equals our kinetic energy final, which we know is 1/2 mv squared. All right. So finishing out, I'm just going to solve for velocity here. I'm going to multiply 2 on both sides and divide by the mass of the proton. So we have 1.6 times 10 to the negative 19 coulombs times 40 volts. That's going to be multiplied by 2 and divided by the mass. The mass of a proton is... um, Does anyone remember the mass of a proton? I way forgot it. It's like 1.67 times 10 to the negative 27, something like that, by chance. Sick. Okay, thank you. 1.67 times 10 to the negative 27 kilograms. Definitely remember that. There's going to be a lot of proton electron questions in there, and you definitely need to know the mass. And we'll square root the whole thing. And that's going to give us the final velocity of our proton when it's at the negative plate. And just to calculate this out really quick. That's very fast. 87,548 meters per second. If you did all your units correctly, then you should end up getting meters per second in the end. Cool. So that's a very common problem. Any questions on how I did it, or are the questions mainly about what if I had a negative charge particle? Okay. I'm not going to do an entire problem with a negative charge particle. I'm just going to do sort of the setup so you can see. So, so if you have it, here's our positive, here's our negative. Let's say we have an electron right here. So this is an electron. So here's really the difference. The electric field of a capacitor always points from positive to negative. So our electric field points this way. but a negatively charged particle feels an electric force in the opposite direction of the E field. So it feels its force going this way. That's because it's getting pushed by these negative charges and it's going towards these positive charges, right? So let's see it this way. Um, yeah, okay. So basically what's happening here is the work done is still just negative change in potential energy. And I'm still going to write that as negative Q times E times our displacement, which is D. But one of kind of the subtleties here is that this is actually supposed to be a dot product. So this is E dot D. When these were parallel in the first case, E was pointing this way, and our displacement, which was going left to right, was pointing the same way. They were parallel, and so cosine of 0 equals 1, and this is just E times D. We have this negative sign here. In this case, electric field's pointing this way. Our displacement, though, is pointing the opposite way, and so we get cosine of 180, which is negative 1. So when I write out the work here, this is negative Q and then negative ED. So negative ED. Negative cancels with a negative, and this becomes QED. Okay. So when I have a positive particle, I'll use this guy. When I have a negative particle, I'll use this guy. You're going to get the same actual answer each time. It's just going to be off by a negative sign. So if I were you, what I would do is just use it like you're using a positive particle. You'll get the correct answer. Then go back and say, okay, do I need to add a negative sign here or not, based on if it's positive or negative? Does that answer your question pretty well? I forgot who asked. Cool. All right. Awesome. So that's a capacitor problem. They're going to be pretty common. Other type of problem you're going to see with chapter 25 material is a bunch of charged particles. So let's say we have three charged particles here. This is positive 5 nanocoulombs. This is positive 5 or positive 2 nanocoulombs, and then this is a negative 3 nanocoulombs. It might give you some distances, like they might say this is 1 centimeter. This is 2 centimeters. And the first question they might ask is, let's say, let's call this our point of interest. For a box here. And they might ask, what is the electric potential at point P? Okay. So I know from everything I know about electric potential that first I have to define my point. So I know it's right here. I know it's my point right here. And if I want to find the net potential at that point, it's just going to be the potential from my 5 nanocoulomb particle plus the potential from my 2 nanocoulomb particle plus the potential from my 3 nanocoulomb particle. That's going to give me my net potential at that point. Now I can go and I can look at what's the electric potential at a point P away from any particle. That's going to be K Q over R, where R again is the distance from Q to our point. So starting off here, potential from our 5 nanocoulomb particle is just going to be K times 5 nanocoulombs divided by the distance between the 5 nanocoulomb particle and my point, which is 1 centimeter. 1 times 10 to the negative 2 meters. The potential for my 2 nanocoulomb particle is K. My charge is 2 nanocoulombs. And then again, the distance is from my charge to my point of interest. So it's going to be this guy right here. If I use Pythagorean theorem, this side is 2 centimeters, this side is 1 centimeter. So that just means that R2 squared equals 2 centimeters squared plus 1 centimeters squared. So R2 squared just equals 5 centimeters squared. R2 is square root of 5 centimeters squared. Okay. So square root of 5 times 10 to the negative 2 meters. Last but not least, the potential from particle 3 is K times negative 3 nanocoulombs divided by the distance between my negative 3 nanocoulomb particle and my point, which is 2 centimeters. So 2 times 10 to the negative 2 meters. So if I put that all together, which I should have done all this separately, I'm going to pull the K out. This is going to be 5 times 10 to the negative 9 coulombs over 1 times 10 to the negative 2 meters plus 2 times 10 to the negative 9 over square root 5 times 10 to the negative 2 meters minus 3 times 10 to the negative 9 over 2 times 10 to the negative 2 meters. I'm going to use K equals 9 times 10 to the 9, and then this will give me my net electric potential at my point of interest. Right, and I get 3,230 volts. Cool. That's going to be my net electric potential at my point of interest. All right. Now, another question might be, What is the net electric potential energy of the system? So in this case, we don't use our point of interest. We're going to do our pairs. Mm. By the way, yes, Andrew, the 10 to the negative 2 is inside the square root. Ooh, no, it's outside the square root. You're right. My bad. My bad. Square root of 5 times 10, negative 2. Don't worry about these numbers too much. I just want you to see the actual physics. Okay. So instead of electric potential, where we define a point of interest and all the particles basically just add at that point, for the electric potential energy of the system, we're going to add up all the pairs for K, Qi, Qj over Rij. All that means is, in this case, we're going to have the potential between, let's say, particle 5 and particle 2. That's going to be added to the potential between particle 5 and particle 3. That's also added to the potential between particle 2 and particle 3. So what that looks like is K for I'm sorry, for electric potential energy here, for the electric potential energy between 5 and 2, that's going to be K charge 1, I'm sorry, charge 5, which is 5 nanocoulombs, and 2 nanocoulombs. And then that's going to be divided by the distance between them. So that's going to be R between 5 and 2, which is 2 centimeters. So 2 times 10 to the negative 2 meters. That's going to be added to the electric potential energy between the 5 nanocoulomb and 3 nanocoulomb particle. So that's going to be K, 5 nanocoulombs, negative 3 nanocoulombs. Now the distance between the 5 and 3, again, is going to be this hypotenuse region, which we decided is the square root of 5 times 10 to the negative 2 meters. Last but not least is the electric potential energy between our 2 nanocoulomb and 3 nanocoulomb particle. So that's going to be K, 2 nanocoulombs, negative 3 nanocoulombs, divided by the distance between them, which is 1 centimeter. So again, what I would do is bring out the K, or our Coulomb constant. And then this is just going to be 10 nanocoulombs over 2 times 10 to the negative 2 meters minus 15 nanocoulombs over the square root of 5 times 10 to the negative 2 meters, and then minus 6 nanocoulombs over 1 times 10 to the negative 2 meters. Okay. And I'm not going to do this one out just because I want to save some time. But that's the difference between finding the electric potential and electric potential energy of a charge distribution. Any questions on that? Cool. What is the final unit, Peyton? I don't know. What is the final unit of potential energy? And anyone can shout it out. What are the units of energy? Yeah, joules. That's why I go through it. And I'm even gonna put, let's say, potential energy, joules, just to remind you guys, joules, because I know it's a lot of different stuff. Electric potential is volts, which is V, also known as joules per coulomb. Uh, yeah, so just remember those two. Cool. All right. Those are the two chapter 25 problems I wanted to do. And then I just have one kind of really big Gauss law problem to do. Okay. So this was charge, this was point charges, and then this was capacitors. You're definitely going to see problems with these two, so I would do most of your practicing for chapter 25 stuff with those two concepts. All right. Last but not least is Gauss law. So the problem I'm going to do, I think, captures a lot of how to use Gauss law. Gauss law. All right. And before I go into it, I just want to give you guys sort of a helpful question tree that I ask myself before I do these problems. So the first thing to ask is, what object is this? It's the first question I want you to ask yourself. So it can either be a box, a cylinder slash wire, or it can be a sphere, which they'll also call a shell or a ball. So those are the three sort of objects or distributions you can get. So first thing you want to ask is, what object is this? Second thing you want to ask, is this an insulator or conductor? Okay. So if it's a conductor, we can use the fact that the electric field is zero inside. If it is not a conductor, or if it's an insulator, then E field non-zero inside. Cool. So I want you guys to ask yourselves these questions every time you do a Gauss law problem. So ask, is this a sphere? Is it hollow in the center? Is it an insulator or conductor? Very last question you need to ask is the object charged, or is there an external charge present? Cool. So those are the three questions to ask yourself. It'll make doing Gauss law problems a lot easier. All right. So let's just knock out this Gauss law problem. I'll answer questions and then we're pretty much good to go. So let's do this. All right, this is a pretty common one. I'm gonna turn the fill off. All right. Okay, so this is definitely one of your homework problems, but I just want to do it because it's so important. Okay, that's fine. Okay, so we have a hollow spherical shell made of metal with a point charge in the center. The inner radius of our shell is A. Our outer radius is B. All right. So first things first, when I'm asking myself questions, I'm gonna go up here. I'm gonna be like, all right, what object is this? This is a spherical shell. When I see sphere, that means when I use Gauss law, when I make my imaginary object, I'm gonna be making a sphere. Okay. What I also know is that it's made out of metal, so this is a conductor. So the E field inside the shell portion itself, the actual shell with some thickness, is 0. So this is a spherical shell. It's a conductor. So now I know what object I need to use for Gauss's law. I also know that since it's a conductor, the electric field inside this actual shell portion, this actual thickness, is 0. That does not mean that the electric field is 0 in this hollow portion. Okay, cool. Well, let's do it. So what they want us to do with Gauss law problems is find the electric field at various points in space. So I'm going to bring up Gauss's law here. Step number 1, it's E dot dA equals charge enclosed over epsilon naught. So first things first, you are never going to have to do an integral. The whole reason we use spheres, cylinders, stuff like that is because we want our electric field to be symmetric with our Gaussian objects. Because they're symmetric, the electric field is constant with respect to area. So we simplify this equation. We can pull out E. That becomes integral dA. And then this simplifies to simply the electric field times the area, and that equals Q enclosed over epsilon naught. And again, all this just comes from electric flux. So that's electric field. That's the area of our surface. And that's just our electric flux right there. Okay. So now the first region I want to look at is I want to find what the electric field is for everything from the start of my charged particle in the center here to my inner radius. So I want to find the electric field for all radius values greater than or equal to 0 and less than or equal to the inner radius A. So to do that, I'm going to draw a Gaussian sphere just inside of radius A. And I'm just going to say my Gaussian sphere has some radius r. Again, that r is between 0 and the inner radius A. So step number 1, I'm going to write Gauss's law. It's electric field, which is what we're trying to find, times the area of my Gaussian sphere. Because again, I'm looking at the flux through the sphere that's imaginary, the one that I drew. That equals the charge that's enclosed by my Gaussian sphere divided by epsilon naught. So all I need to do here is I know that the surface area of my Gaussian sphere is 4 pi r squared, and the amount of charge that is enclosed in that Gaussian sphere is just positive q. So charge enclosed is just positive q. If I divide both sides by 4 pi r squared, the electric field is 1 over 4 pi epsilon naught times q over r squared. I wrote this as 1 over 4 pi epsilon naught because we know that that value equals k, our Coulomb constant. So again, this is the electric field inside our hollow sphere for all r's between 0 and our inner radius a. Any questions on that? Okay. So the part that I want to get you guys to recognize is ignore all the rest of the problem. I know there's a charged metal shell, and you might think, doesn't that interact with the electric field in the center? How can you just ignore everything? I need you to get used to when I say enclosed charge, literally, you just have to look at how much charge is the sphere that I just drew enclosing and ignore the rest of the world. So I drew a little sphere here in my region of interest, which is between 0 and A. And I said, what charge is inside of that sphere? It's only my point charge with a value of positive Q. So that's the only value I take into account when I do my enclosed charge. Okay, I ignore everything else. Okay. Now, here's where people get tripped up. Region number 2. So this is going to be the region where my radius is greater than the inner radius A, but less than our radius B. So this is going to be the entire region inside of my spherical shell here. So I drew my Gaussian sphere, that's in the blue. It has a radius of r. I know that Gauss's law says the electric field times the area of my Gaussian sphere equals the charge enclosed by my Gaussian sphere over epsilon naught. Now, here is where things get a little tricky. And this is why conductors, we have to say that law specifically. So a lot of you probably already know that the electric field in this case is going to be equal to 0. And you might say, wait, you just told me that if anything, if I have a charge enclosed in my Gaussian sphere, the rest of the world doesn't matter. I just focus on that. That is the case, except for when you're inside of a conductor. So that's sort of the exception, and that's why I keep talking about it. So always when you're in a conductor, the electric field is 0. So that's kind of separate from Gauss's law. It's something that you just kind of have to know. Put it on your equation sheet so that whenever you're in that region that's inside the conductor, you know that it's 0. Cool. All right. So it should be automatic. All right, last region. That's going to be all radii greater than our outer radius b. So I'm going to draw my imaginary sphere all the way around. All the way around. Oh, geez. Oh, that's a lot. Okay. Again, it has radius r. Gauss's law says that the electric field times the area of my Gaussian sphere is the enclosed charge over epsilon naught. The area of my sphere is 4 pi little r squared. Now, the amount of charge I'm enclosing is negative q, or I'm sorry, negative 2q plus the charge from our point charge q over epsilon naught. So that means my electric field is 1 over 4 pi epsilon naught negative q over r squared. And this is the electric field for all radii greater than b. Cool. Any questions about that? No, it's kind of a weird part. Okay. So that's pretty much everything I got. Does anyone have any last questions before I let you go? Mm. So that negative 2q is the charge on the entire spherical shell. So that negative 2q is the charge on the spherical shell. And that's why I said one of those important questions is after is it a conductor is the object itself charged or is it neutral? Ah, I see. Yeah, because it's a conductor, that's a great point. If it is charged, all the charge is located on the outside surfaces. Side surfaces. What is the charge on the inner surface of the spherical shell? For that, we might need a little bit more information, to be honest. I just said negative 2q is distributed over the whole thing. Um, a problem like that, they would have to give you a tiny bit more information, like the charge density on the inner surface, stuff like that. I believe that is one of the problems, though. That's in your textbook or either on your homework, something like that. I just wanted to show you one of the more general ones, just so you guys get an idea of how to use Gauss's law. Any other questions? Now is the time. And honestly, the Wi-Fi is doing fine, so I'll put my camera on. Ooh. So Mary asked, is finding velocity of the particle between the two disk capacitor different than the two plate? No, yeah. So it doesn't matter for a capacitor if it's two plates or two disks. It's going to be the same exact problem. Mm. Ooh, Peyton, that's a really good question. Peyton asked, is the charge on the inner surface not induced by the charge inside? So no, because we stated in this problem that we had not a neutral conductor, but a charged conductor. You're going to come across a very similar problem where you have a spherical shell here that's neutral. And that's why, again, it's really important that you ask yourself, is it already charged or is it neutral? If I have a point charge inside of a spherical shell, and this is a conductor that's neutral, what's going to happen here is all the charges that are inside this conductor are going to polarize. So if you remember from the first chapters we did, if we bring a charge close to a conductor, then it's going to polarize it towards a neutral conductor, sorry. So if I bring this positive Q in proximity to a neutral conductor, all the negative charges are going to be pulled to one side. The sum of all these charges is going to equal negative Q. but it's going to be spread evenly throughout the entire inner surface. And then that's going to expose all the positive charges up here, where the total net charge on this outer surface is going to be positive Q. Once again, spread uniformly over our outer surface. So if you have a problem like this, they might ask you questions like, what is the charge density on the inner or the outer surface? For neutral conductor like this, where you put a positive charge in the center, the thing you just really want to note is that, let's say for this outer surface, the entire charge is positive Q, but that's spread over a very large area. So if this is like radius of B, the charge density, the surface charge density, is going to be that positive Q over 4 pi B squared. That's going to be outer. The inner surface charge density is going to be negative Q over 4 pi, let's call that A squared. So the charge is the same, the charge density is different. And that's because it's spreading uniformly over different areas. Peyton's asking if the inner charge was +3 and the outer shell was negative Q, does that cause the inner surface of the shell to be charged to negative 3Q or Mm-mm-mm-mm. So mm, for that one, Peyton, let me do that separately because that sounds more like it's the problem. So I'd have to see like the actual problem. I don't want to get into the weeds of doing that with everyone, but I'll send you an email if you direct message me your email. Does anyone else have any questions about anything? No, pretty good. Okay. Well, I'm gonna stop sharing my screen then. Okay, cool. Well, thank you guys for showing up. I'm gonna post this and then it's just gonna be under that same email, so you can just watch it immediately after it's posted. Or your professor is gonna provide a link too if you can't find it. So anyway, good luck on your practice test tomorrow and good luck on your real test Monday. I'll see you there.
Thank you.
Yeah.
Thank you.
Mhm.